participants able to see the YouTube video live?
Ma'am, can you see it now? Can you just refresh, ma'am, once? Can you refresh, ma'am? It
Just a
is
second.
live, ma'am.
Yes, all right, now it works. Okay, so I hope, I don't know, this is being live streamed, but I hope that the couple of initial minutes, because we have not had any interaction in those minutes.
Ma'am, can you just refresh, ma'am, once?
Yeah,
Refresh, ma'am, it is live, ma'am.
Yes, I can see it now. I think there
Ma'am,
is
please
a lag.
mute the YouTube live, ma'am. Please mute the YouTube live, ma'am. It is echo is.
And now it works. It is muted. Okay, just a second. Okay, so I hope, I don't know, this is being live streamed, but I hope that the couple of initial minutes, because we have not had any interaction in those minutes.
Ma'am, can you just refresh, ma'am, once?
Yeah,
Refresh, ma'am, it is live.
Yes, I can see it now. I think there
Ma'am,
is
please
a lag.
mute the YouTube live, ma'am. Please mute the YouTube live, ma'am. It is echo is.
And now it works. It is muted. Okay, just a second. Okay, so I don't know, this is being live streamed, but I hope that the couple of initial minutes, because we have not had any interaction in those minutes.
Ma'am, can you just refresh, ma'am?
Yeah,
Refresh, ma'am, it is
Hello, ma'am. In your
Yes, I can
system,
see
it
it
is
now.
playing, ma'am. Can you close the window?
YouTube live, ma'am. Please mute the YouTube live, ma'am. It is echo is.
And now it works. It is muted. Sorry about that. I had to just reset the system. I think I had two YouTubes running at the same time. So I'm sorry about that. Yeah, I put it also on my laptop. I started it and then I couldn't, I forgot about that. All right. Thank you, Balaji, for starting the session. And now I think, let me see, my video is on, right? All right. Okay. So I think you can ask me the first question. So all the participants, I see there are a few participants here, and I also received some questions on my via the Google form. So I received them in my response sheet. Before we go into those questions, the people who are here already a part of this discussion, if they want to ask me anything, they can write it in the YouTube chat box, and I can immediately answer. So I hope this course is going very well. I have heard that there are some weekly sessions also by PMRF fellow, and I hope they are being useful. They are very useful to you. If not, of course, you can also write emails to me and so on. Now, the questions that I had received in the response sheet are mainly related to carbon black, which is very interesting because carbon black used to be this material which was not even given much importance. It was like the most inexpensive form of carbon for a very long time. And then new carbon materials came up, for example, graphene or carbon nanotubes, all these advanced nanocarbon materials became technologically important. Then people almost forgot about carbon black, right? Despite the fact that carbon blacks are, if you think about it, some of the first carbon nanomaterials, and they can be bulk produced. And very interestingly, even when you produce them in bulk, they have reasonable size distribution. So this is very interesting. Then now, in the past few years or so, or not few, but let's say 10 years, there has been a new interest in carbon blacks. Carbon blacks are now being used not just for the standard applications where they were used as reinforcement materials for rubbers, but now they're being used for a number of other technological applications, for example, in sensors, in batteries, in electrodes, and so on. Battery electrodes, that's an application I'd like to mention here because we did not discuss this during our carbon black lectures. And I also have some questions related to that. So battery applications are basically the applications where various different functional materials are used. Lithium-ion battery, if you take the example, there are lithium salts that are used for cathode. But sometimes, in order to improve the electrical conductivity of these materials, even though they are cathode materials, not anode, which is, carbon is typically used for anode. But even though they are cathode materials, there to improve the overall electrical conductivity of the mixture. Sometimes carbon black is added. Now you can imagine for battery applications, carbon black needs to be very pure. It also needs to have a reasonable size distribution. If not, it should not be like one particle is 50 nanometer and other is 300 nanometers. So reasonable particle size distribution. But even that is not the most important thing. The most important thing is that it should have a high purity. Now, coming to the first question about carbon black. One question came that, what is the relevance or significance of carbon black, lamp black, the form of carbon black that is produced by inside a tube, for not furnace, but usually there is a cast iron pan on which some oil, typically something from coal tar, the waste material from coal tar, is burnt, and the smoke that is produced, it is not allowed to go out. So, of course, in all carbon black productions, we need to have limited quantity of oxygen, right? So we cannot have so much oxygen that all the carbon burns. So we had limited oxygen quantity, and then it goes through the tube. So it is not allowed to directly interact with the atmosphere. So you can call it also not a chimney, but more like a duct, that kind of tube. So lamp black, although it sounds like you produce in a small lamp in the house, but it's not really, it's a relatively large scale production. Okay, but not as large as, say, thermal black or the other methods of making carbon black. Okay, so what is this used for? What is the significance? Well, significance of carbon black is not just that it's one of the oldest techniques for making carbon black, but also the fact that it can give you a medium scale production. You don't want to go into, thousands of tons of scale. That scale you don't want to go to. So what you want is more like, say tens of kilograms, or even in some cases hundreds of kilograms. So there is less investment in carbon black plants. So you can have, that is one advantage. Small to medium scale production can be done using carbon black. Then secondly, of course, depending upon the precursor and the conditions, you can also control the purity of carbon black. So for example, for battery applications, that's what, I'm coming back to that. For battery and these kind of small scale applications where you don't require, for tire applications, for reinforcement applications, you require a large quantity of carbon black. But in the case of battery or small scale applications, what works better is lamp black because it has, a lower cost due to lower investment. Is someone saying something? Okay, no. Yeah, fine. So that was the question number one, I think, about the relevance of carbon black. And the second question, let me see. Okay, the second question was related to fabrication or synthesis of metal doped or metal containing, if I understand, metal containing carbon blacks. Okay, metal containing carbon blacks, not that I'm an expert, or I have personally not manufactured these things, but I do know that people perform metal doping in carbon blacks. At least I have heard of iron doping in carbon blacks. There are different applications for which you can, battery being one of them, but they can be also fuel cell applications. I think platinum coating also, I've read somewhere that for fuel cell applications, you can coat or dope carbon black with platinum. Now, coating of metals can be done in many different ways. You can also take salts of metal and perform mixing, so salt solutions, and then you can dip your carbon black. If there is reasonable surface energy, then some part of the metal can get deposited on top of that. You can also, if the applications are very sophisticated, then you can go for more sophisticated or expensive techniques like sputtering and so on. But in general, you would use metal salts for mixing or doping. The salt solutions, or even in some cases, electrolyte kind of solutions, so they are also salt solutions. But these solutions can also be electrochemically then deposited on top of carbon black. So yes, it is possible, but the fraction of metal is not too high. Coating is better in that sense compared to doping. So yeah, I hope that answers your question. There was one more question related to that. This was about the characterization techniques that can be used. Okay, so before I answer that question, I also want other listeners, other learners to post their questions on YouTube, because I don't have access to the form anymore. I'm not even sure if the form is open anymore. But I can see your questions then. By the time I'm answering this, maybe if you write your questions, because there is a time lag. So if you have anything or any topic that you just generally want to understand and you want me to explain again, because see, every time I explain something, I explain it completely differently, because I myself don't remember what I had in the slides, whatever story comes to my mind. So if you have anything that you'd like to repeat, or at least give you a general idea, please do post your comments on the YouTube. Okay. So yes, we were talking about what characterization techniques can be used for carbon black, or particularly metal containing or metal doped carbon. So doping, by the way, I personally avoid using this term doping, because doping is something that is done in a very highly controlled fashion, and also usually it is when you're tempering with the structure, the crystal structure of the material. That is when we call it doping. Rather, we can use different terms. We can use terms like, I hope my internet connection, I'm getting a message that my internet connection is no good. Let me quickly move to my phone network. Just give me 1 second. I'll move to telephone network. Yes, hi. Am I audible now? Okay, I'm assuming I am. All right. Yes. So I was sorry about that. My internet was unstable. I changed it now. Hopefully this will work. All right. Question was the characterization technique. So if you have metal present in the carbon black, or any other carbon material for that matter, you can typically perform, you want to characterize the metal. If you want to characterize just the carbon part, CHNO elemental analysis works. But if you want to find out what is the extent or fraction of metal on the surface of your carbon, then EDS, that is a support technique of SEM, that is scanning electron microscopy, right? EDS is what tells you the elemental mapping is done in this technique. So that can give you, because you have carbon black is more in the particle form. So in that case, you can find out. Usually what I would do is I take a combination. Most of my, this kind of characterization work, I take a combination of the two things. So SEM, or the elemental mapping in SEM, will tell you what is the fraction of the metal on the surface. But if you want to know what is inside, then you can also perform other kinds of elemental analysis techniques. Elemental analysis, what is standard elemental analysis is CHNOS. These are the elements. Basically, it is designed for organic materials. But if you know that there is some materials present on the surface, and you can also perform things like ICP-MS. But those are very highly sophisticated techniques, and not everybody will have access to them. Elemental mapping can be done. In my opinion, that is a good idea. If you want to know surface functionalities, then XPS, or X-ray photoelectron spectroscopy. That is also another technique that tells you about what kind of bonds are present in, if there are metals, you can typically detect them. So yes. Okay, any other question? Now I see some more people have joined. Please do ask your questions. Please do post your questions online. If not, at least tell me which topic I should talk about. So carbon black is one interesting topic, but what else? Is there opportunity? Okay, there's something in the chat box. Okay. Now this is a general question. Maybe you should ask more technical question. Is there any possibility to do internship? Definitely there is, but that is something that we should discuss offline via emails or something. You wanted to ask something about carbon fibers. Maybe if you ask me a technical question about carbon fibers, what exactly interests you about carbon fibers? What do you want to understand about carbon fibers?
Good evening, ma'am.
Okay, yes.
And I am interested in cryogenic tanks in which they will be winding carbon fibers, right?
All right. So it is
Definitely.
okay, I understand. So for a lot of cryogenic applications, by the way, also hydrogen storage, different kind of cylinders, lightweight and strong cylinders, carbon fibers are being used. When you say carbon fiber, are you just going to have winding of carbon fiber or carbon fiber reinforced polymer? So CFRP or just carbon fiber?
Right now, I am not clear about it, ma'am.
Yeah, okay. Fine. So this is something very interesting. The word carbon fiber in industry is used for carbon fiber reinforced polymer. This is a very confusing thing. People say that you have a car made of carbon fiber, but it's actually not carbon fiber. It is carbon fiber reinforced polymer or plastic. All right. What you can typically have. So I don't know if CFRP or those lectures have already started. I don't know. But so what is the lecture number or what is the topic right now that's going on in your lectures?
Yes, ma'am. Next video is on carbon fibers.
Okay. So next topic is carbon fiber. So I hope that will make this clear to you. But I'll also give you a little bit of background here. Carbon fiber alone can be manufactured using some spinning techniques. Now spinning techniques are either electrospinning. Electrospinning is something that we only use for lab scale applications or slightly larger than lab scale applications, because electrospinning will give you fibers that are of different diameters. So the uniformity in the fibers is not there. So it's not that they are very randomly distributed, but still structural applications. When I say structural, I mean large scale, like the kind of applications you are talking about, where you will perform a winding or you want to basically give a material, anything, any device, let's say your cylinder or something, you want to provide it with mechanical strength. So mechanical strength basically requires all fibers to be of the more or less same diameter. So we use something called melt spinning techniques, or there are also some other variations, jet spinning, wet spinning. These things I have not discussed in the lecture because already the content was too much. So I have only discussed two main techniques, melt and electrospinning. Okay. If you want to make carbon fiber reinforced polymers or any other composites based on carbon fiber, then you need to use melt spun fibers that are typically only manufactured at a large scale. So usually you will not find them in research labs. So for example, you wanted to do internship with me, but I will not have a melt spinning setup here. I only have an electrospinning because melt spinning is done at a very large scale. You require like huge plants for it and not just one little machine. Okay, that is number one. What happens is carbon fibers that are prepared by melt spinning of, let's say, polyacrylonitrile, and then I carbonize it. Carbonization process remains the same. So it is heating at a certain temperature, definitely above 900. It can go up to 3000 degrees depending on the kind of microstructure that you want in the absence of oxygen. That remains the same. So I heat treat them and I make, I make carbon fibers. Now, if I want to make some structures out of it, then I need to use some polymer resin as a matrix material. Matrix is something that holds your reinforcement. Reinforcement is the material that gives strength, mechanical strength to the overall composite. So I will have carbon fiber, woven or braided carbon fiber. This is something again you will learn in the lectures. Braiding technique, basically making these kind of structures, or so that you can have some sort of mechanical weaving is what you do for your clothes. So those kind of things you do. And then you have these carbon fiber cloth-like structures. And then these cloth-like things can be oriented on top of each other at different angles so that altogether your material or the entire composite, whether you call it material or a combination of a couple of materials, the entire composite has a very high mechanical strength and a very low weight. Okay, this can be wrapped around anything, cylinder, tubes, anything, usually something that needs to withstand a lot of pressure. Because what you can imagine, if you have even few layers of cloth, right? If you have few layers of cloth and one on top of the other, if you keep on wrapping it around something, then that makes the overall pipe or whatever it is stronger, in the sense that it will not explode. And even if there is some explosion, it will not be as the shattered pieces will not go away and things like that. But this is where carbon fiber reinforced composites are, CFRPs in particular, are used. So I hope I've given a long answer to your question. I hope that will become more clear as you go ahead in the next section. Okay. So another question regarding the metal containing carbon blacks. How to identify whether the metals are present as add atoms, as ions? This is a very complicated. See, this is why I was telling you before that metals in carbon don't behave. I was talking about doping earlier, right? That the term doping I personally avoid using, because when you're doping something, then it's done in a very controlled fashion. Then you will have certain type of defects, right? Induced defects, if you want to have carbon very uniformly distributed in the entire system. Now, for that purpose, the first thing that is required is that your carbon itself should be perfect. In graphite, if you have a metal, you can find out whether it is, what kind of defect does it produce. Similarly, even in graphene, and when I say graphene, perfect graphene, single layer, and nothing other than hexagons, so no defects, right? If you now induce a metal into that, you can then evaluate it with respect to the structure or crystal of your material. But that does not happen in the case of disordered carbons like carbon black. So carbon black itself, you cannot define its crystal structure, right? So how are you going to define what is the, where is the metal present in that crystal system? Also, this will depend on what kind of, metal, including metal inclusion method. I don't know how to say it, like deposition or what have you used. Depending upon that, you can have, for example, whether you have used a metal salt as a precursor, have you heated that salt, have you completely decomposed your salt, have you added, have you performed sputtering or something you've added on top. So depending upon that, you will have either ions or different, maybe even oxidation states of the metal, depending upon the metal, right? If you use, different oxidation states of iron can be used. That is a different question. If you want to correlate it with crystal structure, however, then it is very difficult in the case of carbon black, given carbon black is itself a disordered carbon. Actually, there are a couple of interesting articles on how to graphitize carbon blacks. You see, carbon black, it's a spherical kind of structure. So you cannot completely, change it. You cannot completely, what should I say? You cannot completely graphitize it. But at the same time, you can get small graphite crystals from carbon black. It's very interesting. So, yes. All right. So there is now also power cut. Everything is happening when I have my live YouTube session, but we are on telephone network, so it should be fine. Okay, another question. Can you tell about carbon fiber? From economic viewpoint, okay. Price availability. So, all right, that's a very good question. I cannot give you the exact price, and the reason is I myself make the carbon fibers. I don't really buy them, but it also depends. It varies a lot. Carbon fibers can be of different grades altogether, right? Some of them are called high performance or HP grade. So high performance grade carbon fibers have very high Young's modulus. They also have very high the ultimate tensile strength. So they are very good quality carbon fibers and they are used for very high end applications. They are also very expensive, But there are also some fibers that are called general purpose carbon fibers. So GP grade is typically cheaper. Now GP grade will have, in GP grade, sometimes you have a higher Young's modulus, lower tensile strength, or lower, lower Young's modulus and higher tensile strength, or sometimes both of them are low, depending upon these, properties. Then you can get cheaper carbon fibers as well. However, when we talk about research purposes, so as I said earlier, that for research purposes, for example, if I want to make some sort of sensor, or if I want to make a battery electrode from carbon fibers, for these kind of applications, we may end up using electrospinning rather than melt spinning. And then electrospun fibers, if you're doing it yourself, and if you're using a cheaper precursor material, then they can be reasonably expensive. In fact, electrospinning is also a very inexpensive machine. Also, the setup is also very inexpensive. You can also build your own. So yeah, I myself built during my graduate studies. I was building. So all you need is a power supply, needle, syringe, and syringe pump, and so on. Precursor materials, if you want to get very high purity of carbon, then precursor material, the most common precursor material is called polyacrylonitrile or PAN. That is expensive, reasonably expensive. But people have started trying new precursors like rayon, that is a type of cellulose. There are several petroleum pitches available. Pitches are produced as waste material in most of the petroleum or coal tar industry. Different petroleum and coal tar are two different classes of pitches. We don't want to go into the chemistry and the details of that. But pitches are much less expensive compared to polyacrylonitrile. So if you start using pitch or lignin, which is from waste biomass or something like that, in that case, your own, at least the in-house carbon fibers are cheaper. So yeah, that's all I can tell you. If you want to, you also wrote that what is from economic point of view, if I can discuss carbon fibers. I don't know what you mean by that, but in principle, if you see in a broad economic viewpoint, carbon fibers are becoming more and more popular in a lot of new and advanced applications, especially in automobile industry. Carbon fibers are now becoming very important structural material. Okay, and like you said, also for a lot of high pressure pipes and high pressure cylinders, also in civil engineering applications, even there are a lot of cement reinforcement is also done. So maybe carbon fibers in another 20 years or so. Other applications are like wind turbine blades, a lot of number of good applications. The only issue right now with carbon fibers is its reusability, or see, carbon does not disintegrate, right? It's a very, very strong material, strong in the sense not mechanical strength, but also it has very good bonding with itself. It's not a material that degrades by itself, right? You know that even up to 3000 degrees you can heat it in the inert atmosphere, then nothing will happen. If we try to burn it, then it will form carbon dioxide and carbon monoxide, but those are not environment friendly gases. Altogether, it makes it very difficult to recycle or reuse carbon fibers. That is the biggest challenge. But if that can be solved, and even if that is not solved, to a great extent, carbon fibers are becoming very, very popular materials. So in another 20-30 years, that is going to be something that dominates the market. And what is very interesting is, even today, there are not many manufacturers of carbon fibers, at least when we talk about good quality carbon fibers. So lab scale fibers, electrospinning, that is done extensively. But when I talk about these large scale application of carbon fibers, where you need uniformity in terms of diameter, and where you also need very large scale production and winding and all these kind of additional things as well, there are very few producers. I think I could count on my fingers, 10, 11, something like that, all over the world. And very few in India. There's some in India, interestingly, some 20 years back, there was more work on carbon fibers than there is now. But anyway, the point is, carbon fiber has a lot of economic significance, if that is your question. So if you want to start a company, invest in carbon fibers, but you'll have to invest like a lot. Initial investment is a lot. Okay, any other? Oh, yes. Okay, thanks for another question. Synthesis of CNTs using thermal CVD. Okay, I used toluene and ferrocene. All right. I'm facing difficulty in controlling the gas flow. Oh, okay. All right. So your question is fine. You are facing difficulty in controlling the gas flow. That could have something to do with your own system. Because CVD, I have to see your CVD furnace in order to answer that question. But in general, based on my experience with CVD furnaces, is that your mass flow controllers can have some issue. Your gas purity may also have some issue. And it's not just your whatever is your like toluene and precursors, not just the precursors, but also your carrier gas if you have any. If you have any hydrogen, nitrogen, any other gas in the system, their purity and their flow rate also matters. So CNTs will come, this topic will come after, let's say, I think in a month's time, because nanomaterials I teach later. So it's carbon fiber, then graphene, then CNT. Okay, but the important part is carbon nanotubes or any other carbon material for that matter, they have prepared inside a tube reactor. So when we say furnace, then we basically talk about, just a furnace. But when we say reactor, then that basically means it's a slightly large scale, furnace, where the diameter is also a little bit bigger, not like very small diameter. CVD can, in principle, be performed in a standard tube furnace also, but I'm talking about the commercially available CVD reactors that maybe you are using. What is most important? Now, the diameter of tube I have mentioned in particular. The most important thing there is the Reynolds number. So Reynolds number depends on the tube diameter, tube length. It also depends on the overall viscosity of your fluids, and that is also controlled by, or it is indirectly related to the flow or the type of gases, the ratio or the of, for example, ferrocene. All of these things matter. So the most important thing is how do you calculate the Reynolds number of your system and whether or not you have a laminar flow. Typically you will, but if your reactor diameter increases too much and you have wrong pressure, wrong flow rate, in that case you may have some sort of instabilities inside your system, and that can give you bad CNTs. So I cannot answer the question directly about your particular process, but in general this is the important aspect. So control the flow rate. First calculate the Reynolds number, whatever is your system, and ensure that there is laminar flow and as stable flow as possible. You can also check for the purity of your ferrocene. You can try to use just directly iron nanoparticles rather than ferrocene, because I think you're using, yes, in your question it's written that ferrocene is your catalyst. Ferrocene people sometimes also use as carbon source itself, because ferrocene has some organic part also. So maybe the organic part of your ferrocene is not degrading early enough, like your process is starting before your ferrocene can degrade. This is not I have not done this experiment personally. Maybe you already know, maybe you have already optimized these things. But flow you can optimize a little bit further. Also, it is important whether you're using if you're using the ferrocene attached to a substrate, or the ferrocene particles are inside your entire CVD chamber is filled with your particles, or the combination of toluene or whatever you're using. So that will also make a difference. There are two methods again. This will come later on. There is something called seeding catalyst and floating catalyst. So seeded catalyst or seeding catalyst is attached to a substrate, right? And the floating one is floating inside your entire CVD chamber. So also that makes a little bit difference. And especially for carbon nanotubes, people also use floating catalyst method. And carbon nanofibers also, by the way, this I have not, the previous question related to carbon fibers. There is yet another type that I did not discuss because you were only talking about the large scale applications. There is also a third type of carbon fiber, which has nothing to do with spinning techniques at all. it is grown similar to carbon nanotubes. So carbon nanotubes are basically hollow carbon fibers, or you can call carbon fibers, solid tubes. Basically, there is a thin line. Often when you perform the CVD, maybe the person who has asked me this question also is facing the same problems. When you perform CVD, you actually want to get carbon nanotubes, but if your catalyst size is slightly larger, then you may end up getting carbon fibers. So basically, tubes become solid because when there are too many walls in the carbon nanotube, right? At some point, the walls sort of collapse and they make it a solid, or somewhere solid, somewhere hollow kind of structure. So that becomes a carbon fiber. So that's yet another type. That those fibers are very small. They are typically not more than a couple of millimeters length, and the diameters can be smaller. So they are usually in the nanoscale. So those are another type of fibers, but since they are so small, a couple of millimeters, they are not typically used for making cars and these kind of large scale applications. Okay. There is another question, follow-up of the carbon nanotube question. What would be the indication that we are proceeding in the right way? Life, like from the outlet, the color change. See, in principle, indication that you're doing it right would basically, I personally think that if your yield is stable and your process is reproducible, you do two things. Don't even think about whether you're getting higher yield. First of all, just see if you get reproducible yield. If you get reproducibility, that means your system is stable. Okay, and if you don't get that, then in that case, you're not moving. There is still some instability in your system, which means you still need to work on the flow pressure, all kind of, all these numbers. So whether you're going in the wrong direction or not, it's always judged by reproducibility other than anything. Reproducibility means you do the same experiment twice and you should be able to get more or less the same material, same yield. Okay. Okay, thank you too. Okay, some more questions. I'm glad it's a nice interactive session. I have read about paracrystallinity. Okay, short to medium range ordering. I don't know whether you call it paracrystallinity, but anyway. Presence of parallel layers, but no discrete 3D. Okay, in a few articles, this is some type of disordered material. If yes, there is a drastic fundamental difference. So polycrystalline and paracrystalline. See, this is, in my opinion, so I personally never use the term paracrystallinity. I would still call it a disordered form of carbon. In general, it is a disordered form of carbon. Now, what you have written is short to medium range order. There are parallel layers, but no discrete 3D grouping. So this is basically what we are talking about is certain type of graphitizing carbon, right? Graphitizing carbons, what do they have? If you remember again your CVD, when we were talking about HOPG, at that time I had mentioned briefly about CVD. That is the same process. Now we use it for graphene fabrication. But these layer type carbon deposition, but not a long range order. This can typically exist in graphitizing rather than non-graphitizing carbon. Non-graphitizing carbons are basically carbons that will never convert into graphites. Now, by now you should know that. Carbons that will never convert into graphite, because also they have these fullerene-like strongly curved structures which cannot open and things like that. But these kind of parallel layers exist, and they are, although they are, maybe more than 3.35 nanometer in angstrom in terms of distance, maybe they are 3.37, let's say, something like that. So, but they can be converted into graphite. So this is what I think is called paracrystalline, but I personally not heard of this term, and different conventions actually also which field people are coming from, that allows them to speak. So paracrystallinity, maybe something like paramagnetism, maybe where there are parallel structures exist. In my language, I just call it a graphitizing carbon. Okay. All right. So, are you all students like PhD scholars, or you are professionals working for some company? Somebody starting his or her own company? Write it in the chat box, because that will help me understand, whether I should explain things very much, in the fundamental language or a little bit of paper reading language. I'm a BE student, professor. Okay, you BE, just only BE, that is very good. Already you're learning so much about carbon fibers. See, BE in which branch? Is it mechanical or materials or what? Mechanical, I thought so, because you're thinking about these kind of applications. So in principle, I teach mechanical engineering students, and in fact, at IIT Mandi, I rather teach more manufacturing courses than materials courses. Materials and manufacturing are always very closely related, but when we try to learn more about, when we go towards materials, then we have to actually learn more about the fundamentals of like what goes inside your material, what is inside your carbon fiber, what is disordered, what is crystalline, what is different phases of the material, phase diagrams of the materials, and so on. So when we actually go deep into materials, then materials engineering is all about, not just all about, but a lot of it is about understanding the material from inside. However, that knowledge is very important if you want to manufacture something, right? Manufacturing also can be related to metals. So if we don't think about carbons, if you want to make some sort of steel, and if you want to make, let's say, a small part on a lathe machine of high-speed steel or something like that, there also you need to know what are the different types of steel, which one is softer, which one has a higher electrical conductivity, or which one has which properties. Based on that, you will select the manufacturing process. Maybe something can be casted, that is more efficient. On the other hand, another metal may be more compatible with sheet metal processing and things like that. Carbon is a very special case there. Now, carbon cannot be, you cannot perform casting, forging. Most of the standard manufacturing techniques that you learn in mechanical engineering, they don't work for carbon. That is the reason I also find carbon very interesting, because it does ceramic processes, you can say a little bit of powder processing can work, but even that doesn't work for carbon as it works for ceramic materials. Without a binder, it doesn't work. Altogether, what you need to do is make carbon things in precursor materials like polymers, and then you convert them via heat treatment, you convert them into carbon. So that's a very different manufacturing process, but the materials, and also it gives you a lot of flexibility, like you can make fibers, you can make large scale structures, you can make electrodes, graphite electrodes from needle coke, for example. So you can make different shapes, different structures, and ultimately you can convert all of them again by controlling the heat treatment temperature there. Either you're heating it to 900 or you're heating it to 3000. Based on that, you can also control the crystallinity. Certain limitations are there, but a lot of flexibility. So that way, carbon is a very interesting manufacturing material. So it's good that you're taking this course. That way you can also at least learn few fundamental things about the carbon as a material also. Okay. So I got 2 more responses now. I'm a PhD scholar, first year, from University of Petroleum and Energy Studies, Dehradun. I see. Okay, working on graphene synthesis and using CVD for the transfer process. So yeah, this is a very good project, and I have in fact been in touch with some people from this institute in Dehradun. I used to be also, I did my internship long time back. Anyway, the thing is, if you're working on CVD, graphene synthesis, also your question was related to carbon nanotubes. So graphene carbon nanotube synthesis is a very interesting area. There is still a lot of scope for understanding the fundamental principles. So it's not just about large scale production. There are a lot of applications that are already established. A lot of large scale manufacturing processes, manufacturing plants are even there. But what is still missing is the fundamental mechanism of the formation of carbon nanotubes or graphene. So there are certain models or certain theories that exist, and those are theories I've also covered in my lectures. But still, there are few more details that people need to know. What is the exact influence of catalysts? For example, graphene can be deposited on both copper and nickel. Typically, it is believed at least that one of them has only surface migration of carbon atoms and the other has the, carbon atom goes a little bit inside. Then there are theories also related to formation of carbides, particularly for the case of carbon nanotubes. That carbide is formed and then it is precipitated and then carbon comes out. But still there is like more information will definitely be helpful. So if somebody like you is working, once you get a control on your CVD reactor and you're able to use different parameters reproducibly and you're able to control them to a great extent, then you can understand which catalyst gives you what, which which precursor gives you what kind of carbon material. Precursor actually doesn't matter so much, but it matters for controlling the reaction parameter, but ultimately you just need a source of carbon, doesn't matter what. But catalyst is very important and all the reaction parameters. So this is good field to go. In my opinion, you should focus not just on the application, but you should also try to understand some fundamental things. There is a lot of scope and I want somebody to do it. I'm not doing it, but I'll be very happy if one of you can find out and tell me the exact mechanism of graphene formation. Okay. Okay, so one more learner, he has done his postgraduate in material science and engineering. Okay. Right now conducting research on synthesizing especially carbon blacks for electrochemical applications. Yeah, so that is perfect. So you're working on some project which is basically about carbon blacks. First of all, it's a good idea to work on a project before you decide on your PhD topic, because it's good to know what you're getting into, because it's very important that you love your PhD project. I mean, just really, PhD is not something your guide can force you to do. So you need to be interested by yourself. So if you're already working on it, that's wonderful. And you seem interested in carbon black and also other carbon materials. Carbon black is interesting because one thing I told at the beginning of this video, that it is a nanomaterial which was not first considered as nanomaterial, or its applications were not, people never thought of it as a sophisticated fancy material, but nowadays people do use it for very high-end applications. That is number one. The other very interesting thing that I find about carbon black is its manufacturing process. You see, all other materials, carbon materials, they are manufactured using completely, very strictly inert environment. Carbon black is one thing, but the strict, oxygen-less, oxygen-free environment is not required, because indeed you have a certain amount of burning. You induce a little bit of burning, you use a little bit of oxygen. That is what makes your carbon, that helps in controlling the size of carbon black and makes it very fluffy. Because you don't get this, the carbon atoms or the small fragments that are formed, they don't get enough time to make nice crystals, right? They are fluffy. They're very fluffy there on top of it. So this is what the use of oxygen, the role of oxygen in carbon black formation is very, very interesting. So that is yet another. So carbon black, again, usually people would not make it in the lab. Most people buy carbon black. The reason for it's not that it's very difficult to make it in the lab, but it's very difficult to control its properties and size in particular, also agglomeration and things like that. It can better when it's manufactured in large-scale plants, because there are multiple different filters through which you will typically remove or get rid of the larger particles. So at industrial level, it's we are already what we buy, then we already have a good particle size distribution. We know what we are buying, also electrical properties, all the properties we know. If you want to make your own carbon black, possible, but it may the purification of it or the size segregation of it might take a very long time. Now, if you're using it for electrochemical application, this is actually it's not that in the past people did not use any carbon black. Often carbon black was mixed in. So if you know of the history of batteries, also, it's very interesting. So for the past almost 200 years, batteries that are used for some sort of technological application have existed. And more or less in every battery, in some form or the other, carbon was used. Carbon also brings a little bit of stability when it comes to batteries. So if you have only zinc and copper, or if you have any just metal-based batteries, maybe they may corrode very fast. Also, you may find it difficult to control their parameters. But with carbon comes a little bit of material stability as well as corrosion resistance and so on. So carbon has always been, powders of carbon of different type, graphites, that have always been used in electrochemical applications. And they're also being used today. Now, the only thing that has changed is the form of carbon has changed. Carbon blacks also have become much more advanced than they used to be in the past, better size distribution. Because nowadays we also have a lot of characterization techniques that can give us more reliable information and things like that. Forms of carbon have changed, but carbon still remains an important material for all electrochemical applications, not just battery, also supercapacitor, this and that. Okay. Okay, that's a good question. What fascinates me the most about carbon? I don't see this one single material can take so many different forms, right? It's just one material. No other material gives you that kind of variety, let's say, right? And that is number one. And number two, there is still a lot of scope, a lot of work needs to be done on carbon. When in the very beginning of this course, I was talking about carbine, right? SP hybridization. How much do we know about SP hybridization? Nothing. SP hybridization in elemental carbon. We know about SP in whatever, some polymers or some kind of organic materials, but how much do we know about carbines? How much we know about SP? Is there any SP hybridized material in bulk carbon, like any non-graphitizing carbon? Yes and no. I myself don't know. So there is so much work. It's like we don't know anything about carbon, despite the fact that we know so much about it. So that is something that fascinates me about it. And of course, there are a lot of applications, and applications also often have industry interests or money involved, but that doesn't interest me. That part doesn't fascinate me. What fascinates me is that we know so little about this material. Okay, somebody also asked me a question. We are looking for thermal CVD facility for growth of monolayer graphene on copper. We have CVD, but rapid cooling leading to modified. Okay, if you have, please. Okay, I will check this out. And why don't you write me a separate email with your requirements, so I can check it out. We do have a CVD facility here. But right now, what is the status and what are the regulations for external users and all that? Then if you write me an email, I can give you a detailed answer for that. Okay. All right. So it is almost 6:30 now. If there are any further questions, let me know. I thank you guys a lot for coming here, because this was a very fruitful 1 hour for me as well. I like to talk to people about carbon. And I like to, it's not even that I'm trying to motivate you, I'm just sharing my experiences with you. And I personally really enjoy working on this material. So it's nice if other people are also, they also have the same interest. And what is also interesting is, you can work on one type of carbon mix. So I see somebody is working on fibers, then carbon black, and then there is a third participant who's working on CVD, so nanomaterials. These three types of carbon materials are actually very different, but if you try to understand the very fundamental principles of this, manufacturing process in itself may look very different, spinning setup compared to a CVD reactor or black process. They can look very different in terms of the machines that you use. But the fundamental principle in all the cases is exactly the same. You have an organic material, you remove everything that is not carbon, then you get carbon. The rest of it is just technology, right? So this is the fascinating thing about carbon, and I hope this course motivates you to do more work on carbon. And please do write to me anytime you have any questions. Also put it on the forum, the NPTEL. You have your one page, the discussion forum for your course. So you can definitely post your questions there. I have responded to a few of them. Can you give some information about internship? Internship also, please do write to me separately, and I'll give you all the details. And I'll also tell you what are the problems with it, what are the good things about it. Definitely, I'll take care of that. Please do write to me. My email ID you don't have. All right. So what you can do, my email ID is Swati, SWATI @iitmandi.ac.in, which you can very easily find if you just Google my name or you go to IIT Mandi web page. Then you can search for my name and the contact details are available there. So yes, for internship, for any kind of using the machine, all these kind of things, you can just write to me. Anything else also, of course. Okay, fine. All right, thank you. Should I close the meeting now? Balaji, is NPTEL okay? Bye. Somebody sending me a bye hand. I don't know, emoji, whatever it is called. Balaji, can we close the meeting now? Okay, maybe I will just leave the meeting. I think we all leave the meeting, then the YouTube link will automatically stop. So thank you very much. Thanks again. And maybe we'll have one more session later on.